Hello, my AP Chemistry students. This week starts a new lesson called Electrochemistry. And basically, there are some reactions where there is an exchange of an electron. This is how we make electricity. They are called oxidation reduction, okay, or for short, they're called redox reactions. And this is going to be the start of your worksheet, all these notes. And here's how you can remember which is oxidation and which is reduction. Okay, oxidation, oil, oxidation is loss. Reduction is gain. So here I take a bromine ion. So there's my negative ion. And it makes a bromine atom and it kicks off an electron, okay, but I have two ions, so it kicks off two electrons. Why? Because this is diatomic. So basically, when I lose an electron, my electrons are products. People make a mistake where to put it. If you look at your math, I have two negative here, and this is nothing, and I have a two negative on that side. So if you double check your math, you can see that your charges should be equal, okay? Reduction is gain. Here I have a 2 plus my two electrons that I'm gaining, and that makes no charge copper, okay? So if I do this, I have 0 equals 0. So double check your math when you write these half reactions, okay? Now, if I look at this, my copper, I'm going to erase this so you can see it clear. My copper started out with a 2 plus, and then it went to 0. This number became less. The number was reduced. That's an easy way to remember what's reduction when you look at just the numbers, okay? But why did the number become lower? Because I was gaining negative things. I was gaining electrons, okay? So here's just something I put on for you guys to look at, okay? And I want you to pay close attention to that math. Here I've done the math for you again. And now we need to know how to assign these oxidation numbers. Well, first of all, you can see if it has a charge, the charge is really your oxidation state. Why don't we call it a charge? Because some of these are covalently bonded, and technically they don't have charges, so it's really a bookkeeping method. So here are our rules, and once we get into doing this, you will see it's going to become pretty easy, okay? Any pure element, including diatomics, here's the mistake, all have an oxidation number of 0, okay? So iron is 0. Oxygen, this is considered a diatomic element. Any element is 0, okay? All oxidation numbers in a compound must equal 0. Why? Because compounds have no charges. So H2O, okay? Hydrogen is a +1, but there's two of them, okay? And oxygen is -2. And that's going to equal 0. Why? Because my compound is 0. Polyatomic ions have charges. Okay, so let's look at our OH minus. My oxidation state is always going to equal this, whatever the charge is on there. And if I look at this, oxygen is almost always a -2, hydrogen's a +1, and that's going to equal -1. And as you can see, our hydroxide ion, our polyatomic ion, has a charge of -1. Everything else is pretty easy. It's just the charge that you see, right? Lithium, sodium, that's group 1. They all have a +1 charge. I don't like this focus. Still don't like that focus. Okay. If I flip this over, calcium is in the +2 group. It's an alkali earth metal. Those are all +2. Oxygen's -2. Fluorine, chlorine, bromine, iodine, those are all -1. Okay. Now, some of these can change. What hardly ever changes is hydrogen is almost always a +1, and oxygen is almost always a -2. So when you see those, you're going to automatically put that down and calculate what the other ones, like calcium, can change. Okay? So you're going to always start with these numbers and figure out the rest. Hydrogen and oxygen only have a few exceptions, okay? And I don't think they will ask you anything about this. Sometimes hydrogen is with a positive metal. Well, then my hydrogen's a -1, okay? And these are metal hydrides. If oxygen is in a peroxide, it's the only time it's a -1. So here hydrogen's a +1, but there's two of them, so +2, -1, -2, and then that would equal 0. Okay, so I really don't think they're going to show you those exceptions. Reason being is electrochemistry is actually one of the units they took out, except for this part. This part goes with the recognizing equations in one of the earlier units. Okay, so this part you have to know. So let's start with some examples here. We have our hydrogen. I put my +1, and then you're going to do your halogens next. Those are almost always what you see. So that's a +1 and that's a -1. And notice this is a compound. It has to equal 0. Now, there are 3 bromines, so 3 times -1, I have a total of a -3 charge with my bromine. There's only 1 hydrogen, so a +1 with that, which means my carbon would have to be a +4 for it to all equal 0. Okay? If lithium chloride is a compound and it equals 0, what does lithium have to be here? It has to be a +1. Okay? This is my hydroxide ion, which I did when it's an ion. What is the total going to be? It's going to be a -1. Hydrogen is a +1, oxygen's a -2. That's going to give me a total of a -1. Okay? Chlorine. Right here, we're just putting the charge for 1. Down here, we have 3 oxygens times the -2, so that's a -6. This whole ion has a -1 charge associated with it. So what does my chlorine have to be? It has to be a +5. Now, normally you would say chlorine was a -1. This is one of those things that changes. We always do our oxygen first, then figure out the rest. Okay? If there are multiple things, we do our oxygens, our hydrogens, and then our halogens if they're there. Okay? Here's our manganese. We have 4 of them at a -2. That's a -8. This whole ion has a -1 charge. It has to be a +7 equal that -1. Okay? You can go through and look at these, how I got them, but this is manganese, and here's manganese again. Here's manganese with, it's a compound, it's manganese oxide. And our oxygen has a -2. We always start with oxygen, so that's a -4. Here, manganese has to equal a +4 because this is a compound that equals 0. Notice my manganese has changed charges, and that's one of those transition elements. Those change charges quite a bit. Okay, so I want you to practice. This is your next sheet here. Do what you're going to do. Let's do the first one. Oxygen's a -2. Which means I have a total of a -6. This is a compound, so it's going to equal 0. Okay, so if that's a -6, this is a +6. But notice, +6 is for N2, for 2 of them. So N alone is a +3, right? Because there's 2. So +3 and +3 equal +6. This is a -6. Oxygen's a -2, but there's 3 of them, so each oxygen is a -2. So my N there would be a +2. Okay? Now you have to recognize your polyatomics so you can figure out what's going on. This is a sulfate. It's an SO4 2-. Okay? So we have a -2 here, which means I have a -8, but the whole thing has to equal a -2. Which means my sulfur must be a +6, right? And if this whole thing is -2, this has to be +2. But in any case, my sulfur is a +6. There's only one of them. It carries that whole +6 charge. Okay, so here for my hydrogen, that has to be +2, but there's 2 of them, so my hydrogen's a +1, just like it always is. So make sure that when you want to find the charge, you find it for one atom. This is for nitrogen, 1 atom. +6 goes with 2 nitrogen atoms. And make sure you pull out your polyatomics if they have a polyatomic in them, okay? Is there any more in here? Here, this is a polyatomic, so you would put a -2 there, you'd put a +1 there, because we start with oxygen and hydrogen first, so that's a -8, and then I have my S, whatever that is, and that's a +1, and that whole ion has to equal -1, so -8, -7, so this is going to be a +6, and that's going to make a -1, right? +1 +6, that's +7, -8 is -1, so my S is going to be a +6. Okay, those are a couple of the more difficult ones in there. Here is a polyatomic here, so you need to figure out what the charge is on that polyatomic to figure out what manganese is with the polyatomic. Here I put a little hint. Remember, all pure elements are equal to what? These guys are pure elements, okay? We got diatomics. P4 isn't really a diatomic, but it's considered just one element together. Okay? And those should be relatively simple for you to go through. If you have a problem, give me a private message. I'll hop on this worksheet with you. We'll type together and you'll be able to figure it out. Okay. Why do we need to know our oxidation numbers? This is part 2 of our lesson. We have 3 parts to this lesson. We need to identify the species that's being oxidized and the species that's being reduced. So if we label this first, we can see which is being oxidized and which is being reduced. Okay, so carbon, why do they have a -4 there? Because hydrogen is a +4. Oxygen is an element, that means it's 0. They wrote it kind of funny here. Oxygen is a -2, but there's 2 of them, so it's a total of -4 plus 4, that equals 0. Okay, and oxygen here is a -2, hydrogen's a +1, and we can just look at these numbers, okay? My hydrogen here, this is a +1, it's a +4 because there's 4 of them, but we're looking at the actual oxidation number, so hydrogen stays the same, +1 +1, not being reduced or oxidized. 1 carbon is a -4 here, and 1 carbon is a +4 here. This number went up, right? If my number goes up, it's being oxidized. Okay, oxidize is loss of electrons. I know that sounds tricky, but when I lose electrons, my number becomes more positive, right? My oxygen goes from a 0. This is where it's really easy to figure out. One guy's being reduced and one guy's being oxidized. If you have a lone element, it's 0. Over here, it's a -2. My number decreased, so my oxygen's being reduced. Okay, so here we can figure that out with lone numbers. Chromium is a +1 here. Tin is a +4 here. Chromium is a 3+ here, and tin is a 2+ here. Chromium goes from a +1 to a +3, right? Did my number go up or down? If it went up, it was oxidized, so chromium is what's oxidized here. My tin goes from a +4 to a +2. My number was reduced, so tin is what's being reduced. Okay? Now here is where we have our elements. Don't forget our element is 0, and here it is going from 0 to +3. My iron's going up, right? So my iron was oxidized. Here, my mercury, that is a diatomic element there. That's 0. Elements are 0, and I went from a +2 to a 0. My number became lower. The number was reduced. Why was mercury reduced? Because it gained electrons. It became more negative. It got more negative things. Okay, so that's part 2 of that lesson. And now we want to talk about half reactions, because you are supposed to be able to balance a half reaction. Okay, so now here's the part that you don't need to know, but it doesn't make sense why we're breaking this up in half reactions unless you know what's going on. This is a galvanic or a voltaic cell, and basically I have my zinc metal in there, and I have it in solution, and I have my copper metal here, and I have this in some copper solution because these are copper ions. You can see my zinc is an ion here. Why? Zinc is losing electrons, which means it comes off and turns into an ion and goes into solution. So my zinc atoms are falling off here. They're being reduced. They're being oxidized. They're losing electrons. Oxidation is lost. So oxidation occurs at the anode. You do not have to know that, okay? And these electrons go through this wire, and then I have a bunch of electrons hanging out on this copper, but I have some copper ions, 2+. They want 2 electrons, so they plate on the copper, and that is reduction. It gains those electrons, okay, so we go from a 2+ to a 0. The number goes lower. It was reduced. Reduction occurs at the cathode, okay, and you can see the anode actually gets smaller. Those zincs fall off into solution. Why? Because they lost their electrons. They were oxidized. The electrons come over here, and the copper starts plating on. How do I remember this? I remember this using the analogy crap. Cathode is reduction and product. The product plates on the cathode, which means it was reduced. Okay? Reduction and product at the cathode. Crap. Crap forms on the cathode. Okay? That's how I remember it. This stuff you don't have to know. But because we separate these and get our electrons to flow this way, we use the salt bridge to keep our charges balanced, because if all my electrons built up over here, sooner or later the reaction would stop. But what you do need to know is these half reactions and how to put them together into a total reaction. Here's my zinc. My zinc lost electrons. It became zinc ion in solution with 2 electrons. My copper gained 2 electrons and became a copper solid. When I put these reactions together, you can line them up, they'll add up. We have our 2 electrons cross out, and we have zinc solid plus copper in solution is going to give us zinc in solution and copper solid. That's what happens. So I take these 2 reactions, I add them up. I have 2 electrons here, I have 2 electrons here, they cross out. If my electrons don't cross out, if this was a 1 and this was a 2 or whatever, I would have to multiply the whole thing until my electrons could cancel out, because electrons can't be in our equation. Now, if you want to know more about this cell, here is a YouTube video. It is by far the best explanation I have ever seen. I've never seen anything better. As a matter of fact, people get very confused on oxidation reduction reactions, but not when they see this video. They think it's super easy, okay? Now, this is the only kind of reaction that you're going to have to balance. There are other reactions where, because it's an aqueous solution, I can put water on one side and I can balance it out with H+ if it's acid, or OH if it's basic solution. We're not going to do that. I'm pretty sure they're not going to test you on that, but if you want to learn about it, here's another video about that. So let's finish up on how to do our oxidation reduction, and this is a good review of our single replacements. First of all single replacements are redox. We're going to call it redox, oxidation reduction reactions. Okay, so if you see a single replacement, it's a redox. It's an electrochem. If you see hydrogens and hydroxides being switched around, that's an acid-base reaction. If you see everything in aqueous solution and it forms a precipitate, that's a precipitate reaction. And they're going to want you to be able to distinguish between those. Okay, so first of all, in our let's just go back really quickly and look at our single replacement reactions. I don't really have a good one. Let's look at, let's say I take silver plus sodium chloride. That's going to make silver chloride plus sodium. Now, how do you know right away that's an oxidation reduction? I've got a lone thing here. The silver, if it's an element, it's 0. And here it's a +1. So whenever I have a lone element that then joins a compound, I clearly have a change of oxidation state, and I have a oxidation reduction reaction. Okay, here my sodium's a plus, or here my sodium's a 0 because it's an element, and here it's a +1. They changed oxidation states. It's redox. So if you see a single replacement, it's redox. How do we know if the reaction will happen? If the metal, remember that's our single person who goes to the dance, can kick out the ion in that couple compound. If it's on top, it wins, okay? Here's calcium, and here's aluminum that has that has a charge. Calcium, the lone calcium is above aluminum, so yes, there's a reaction. Okay, remember we're looking at our lone metal. Can our lone metal kick out that ion in the compound? Okay, so do those. Nice review of our activity chart there. Notice our activity chart puts everything as an oxidation, right? We had lithium, it lost an electron, became positive, there's the electron it's lost. Now, you need to be able to decide which one's going to be oxidation. Okay, so oxidation is the top guy. Okay, so we have iron and lead. Here's iron and here's lead. Iron's on top, so iron's going to be oxidized and lead is going to be reduced. Okay, so iron is written just, here's my iron, okay, it is going to lose an electron, and we're going to write it, iron can have multiple oxidation states, but we're going to write it just like it is here. Okay, so this is an oxidation of +2. So Fe2 plus, how did it become +2? Because it lost 2 electrons. Oxidation is loss. Okay, and now we have our lead. Our lead is the reduction, so it's the flip of this. Our lead is going to start as an ion, and we're going to use the 2 because it's there, okay? 2, plus it's going to gain 2 electrons, that's reduction, and it's going to form our lead metal, okay? So now we are going to balance this. Iron goes to Fe2 plus 2 electrons. Now my electrons work out. I've got 2 on this side too, right? So Pb2 plus 2 electrons is going to yield lead. And now I just add up my things, but my electrons are on both sides of the equation, so they cancel out. So iron plus lead 2 plus is going to yield iron 2 plus ion plus lead. Okay, now down here we have copper and silver. Okay, copper is above silver. Where's my copper? Here's my copper and here's my silver. Copper's on top, it's going to be oxidized. So we wrote it as our oxidation. What did it do? It lost an electron. Silver is going to be the ion. It's going to be in a compound, but in solution, net ionic equation. So it's going to lose it's going to gain that electron because reduction is gain. Remember, oil, rig. Oxidation is loss, reduction is gain. Okay? Now, we have 2 electrons here, but only 1 there. In order to balance, my electrons have to be the same number, so I am going to multiply everything by 2 on my silver side so I can get 2 electrons, and then I'm going to line them up just like this, okay, and my 2 electrons cancel out, and then what's left? Copper plus 2 silver ions is going to make copper ions plus 2 silver metal. Okay, so that's how we do it. And you have just 4 to do on your own. So they may ask you to balance these half reactions, and they may ask you to tell them what was oxidized and what was reduced. If they have a half reaction, you can see which one loses or gains, or you're going to look at your activity chart, and the stuff on top is oxidized. Okay? So that is our final new thing to learn. Everything else from here on out will be a review. I cannot get to everything. We're not going to class every single day, so you should be reviewing any videos that I would skip on your own. They do start with acid bases. You don't have to know much on acid bases other than make sure you can identify that reaction. Okay? Everything else is pretty much canceled out. They canceled that unit. Okay, so what you do need to know, and I'm going to read this straight from the book, titration reactions can be used to determine the concentration of an analyte. So you'll have to know your titration equation, which is MV equals MV, or MVA divided by A, which is your coefficient, equals MVB divided by B, your coefficient, okay, and figure out how, your molarity of acids and bases, and those things that we did. You do not need to know strong acids, strong bases, or do any ice charts for acid bases. You will have to do ice charts for equilibrium though. Okay, and then the last thing you need to know for acids and bases is your definition of your Bronsted-Lowry acid proton donor, base is the proton acceptor, and you need to know that they ionize in water, how they ionize, draw those particle diagrams, and do your conjugate acid-base pairs. That's everything you need to know about your acid bases. All the weak acid titrations, weak base titrations, and those calculations are no longer on the AP exam due to COVID. Okay? Talk to you later. Bye.